source that is either deterministic or stochastic. We change parameters and so on. And then on the output side, we're going to watch observers. So we have drag, lift. If you do acoustics, you have acoustic radiation. If you do combustion, you monitor the NOx output. And then you link the input to the output through the system. Okay, so it's basically just poking the system and see how it reacts. Now, usually what we do with the physical system, it's a little bit too complex to do it in all its complexity. So we're going to do usually 3 different categories. And that one is we linearize around an equilibrium point. And then everything is a little bit easier to analyze around the equilibrium. That one is usually the mean flow case. Or we're going to reduce it to essential mechanisms. So the flow is too complicated. We try to really whittle it down to only the things that make most of the mass and energy. Okay, so this one falls under the category of model reduction or mechanism selection. And then the other thing that we want to know is we want to know a little bit about the robustness of the system. Will it fall apart if we change that? Of matrix functions, for example, resolvent analysis is a very popular way of seeing what happens around the linearization point. Reducing down to essential mechanisms, we also have a whole toolbox of standard techniques. POD, TMD, Koopman, SPOD. If you want to go a little bit more complicated nowadays, operator inference, or now with machine learning. There's also ways to do that. Adjoints come into play. If you do it linear, you use adjoints plainly. If you do it nonlinear, you do adjoint looping and checkpointing. You use Lagrange multiplier, or if your code is differentiable, then you use automatic differentiation. You get all kinds of sensitivity information out of your physical system. Now, I gathered all of that one on the standard, okay, because it may take a lot of effort. Maybe one of the techniques is quite modern, for example, operator inference. But I want to go off the standard and show you 4 techniques that don't fall into the standard category. They all have a little bit of a twist that makes them non-standard. And that's where the non-conventional analysis comes from. So, on the linearization side, I basically ask the question, what happens if there is no point to linearize about? Okay? So the system does not have a well-defined equilibration point. We have a system that has multiple equilibrium points that are all equally important. Okay? And if you average all of them out for a mean flow, you get a state that is never observed. What do you do then? None of the standard techniques will come into play. The second one is the second tool will be on the model reduction side. So I'm going to show you how to residualize the latent space dynamics once you have an extreme truncation. You go for an extreme truncation of the dynamic system. What do you do then to keep the truncated system stable? And I have to show you a new technique that is dynamics preserving reduction. So this is a very specific model reduction technique that preserves the temporal dynamic of your snapshot spaces. Okay? And then the other thing is when you differentiate, that one falls in the differential category. What happens if you cannot use any of these 3 techniques? The adjoint is always defined, right, mathematically defined, but it may not be practical to actually derive the adjoint equation. What do you have? If you have a moving contact line, what do you have? Phase transition. What if you have bubbles, drops, topology changes? The adjoint becomes very, very, very complicated. And adjoint looping is basically, it's an existing technique, but it's not very practical technique. Is there something to replace the adjoint part by something different that is more practical? And in that case, I'm going to show you how to do ensemble variational methods. So naturally, the talk falls into 4 it's preserving reduction, that one is called turbulence is another one where you have certain equilibrium states, they look like a quasi-equilibrium, and then suddenly the whole thing collapses and bursts. Okay? So sometimes we have two competing quasi-equilibrium that are equally important, and we have a switching between, and sometimes we have two quasi-equilibrium states where one is dominant and the other one is kind of a violent excursion. For example, rogue waves or acoustic bursts. Okay? So how do we deal with this? Linearization about a base or a mean state becomes physically totally meaningless, because if you take just analysis. This is joint work with Florence Marcotte and Yannick Ponty from the Université de Côte d'Azur in Nice. Okay, so the way we do that one is we're going to go first of all into phase space. Why are we doing this? The advantage of phase space is that if the phase space is large, by happen every 180 to 200,000 years, and we have seen, I think, recorded 19 of those since we know about it. Okay, so 19 times the Earth's magnetic field has reversed, and the last one was 780 years ago, 780,000 years ago. Sorry. Okay, so if it happens every 200,000 years, we're long overdue. Okay, but you never know with intermittent states when the next thing happens. So here is another picture, a little bit from the North Pole. So we're somewhere here, and we're going to go on a straight path right now over to Siberia. So people are very interested in that. Maybe this is the coming of a new reversal. Nothing to worry about. The reversal takes about 1,000 to 10,000 years to fully go to the southern pole. But during that time, of course, it's very disruptive when the magnetic field more or less points right out from the equator, we don't have the von Allen shield that shields us from all the bad stuff from the sun. So all the particles from the sun will not bounce off and will come straight to Earth. And then if it happens, everybody is maybe gets skin cancer or something. And it certainly disrupts a lot of things. Also communications and all the electronics is going to fail and it's going to burn out and all these things. Okay. All right. So this is our model here. We have the magnetic Taylor-Green model. So we have the Navier-Stokes equations, the hydrodynamics, and then we have a magnetic field that we add on, and the two are linked. So this is mass conservation. Diff of u is 0, diff of v is 0, and we have no magnetic monopole, so diff of b is also 0. And then we're going to link the two, and then we're going to simulate that one in a triple periodic 64 cube box. So this is the part that Yannick is doing. Okay. So if you do this one and you watch out for the magnetic field, the Bx and the By, the two components of the magnetic field, this is what you get. Okay? And if you just do a sine curve on that one, sine SIGN, not a sine, cosine sine, SIGN curve, this is what you actually get. So you see that the magnetic field can be in 4 quadrants, Bx and By. So positive, 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 negative, negative, positive, and negative, negative. That's the 4 quadrants. And you see that from a quadrant analysis that intermittently we go through these 4 quadrants. I should also mention that our reaction coordinates is the average, it's the mean Vx, Vy, so that's the velocities, and the magnetic field, Bx, By, averaged over the bottom 1/8 of our cube. Okay, that's our reaction coordinate. That's how we somehow bring the high phase dimension down to just a few numbers. All right, so if you do that in phase space, and I'm going into a 2-dimensional phase space, even though it's 4-dimensional, okay, this is Bx, By, and then a simulation starts out here, and then it goes here, and here, and here, and here, and switches around randomly. You already see that we can, just to the naked eye, we can already make out persistent states in these 4 quadrants, and then transitory states where you go through really quickly to change from one quadrant to the next. Okay? So how do we analyze this whole thing? So we go into a 4-dimensional phase space, even though I just showed a 2-dimensional one, and we're going to discretize phase space into uniform hypercubes. Okay, so we have a 4-dimensional hypercube, and each evaluation of a snapshot falls into a specific hypercube in 4-dimensional space. Okay, and we're going to trace this one. So this is our hypercube. So our evolution equation is here. Maybe there's a snapshot in this hypercube. Then we go here. Maybe 4 snapshots are in this hypercube, and so on. And we're going to trace out our entire simulation. We introduce new hypercubes as they get populated, or we add them to the ones that are already there. Okay. So if you do all of that one, this one is a discretization now visualized in 2D. We have basically a placement of all the snapshots of our simulations in phase space. But that one doesn't have any time information, okay? Just the population. So the time information comes from using a Liouville equation, which is the inviscid part of a Fokker-Planck kind of system, that says that the snapshot density in phase space is given by F, which is the flux function. This is our Navier-Stokes and magnetic equation together. Okay? And that one brings in the evolution part, the time part, again, by just using this model equation as our underlying governing equation. Now, if you write the integral form of this one, okay, then over one time step, so s minus 1 is one time step back, if you integrate that density for each little cube, okay, and you show where this one comes from, so you stick in this equation here, you can define an operator that brings the density of your snapshots from hypercube to hypercube over one time step. Okay, so we're going to have here an average or a density in this one, and then we're going to go one time step back, Okay, we're going to trace all the snapshot that ended up here to the previous snapshot. Okay, and that one traces out a other density cube in that sense. Okay, and then we're going to see this little part here was already in the cube that we ended up with, but this piece came from the neighboring cube, this piece came from the neighboring cube down here, and this little piece came from the neighboring cube up there. So I can basically describe over one time step the motion of the probability density of finding a snapshot in that cube. Okay. So if you discretize this one, this was the integral version of a Liouville equation. If you discretize one, what do we need to do? We need to basically count all the events where we end up in box BI, and one time step ago we were in box BJ, the neighboring box, divided by all the snapshots that end up in BI. So this gives us a probability of coming from a different box, from I to J, okay, over one time step. Okay. So if you do that one, this one is the matrix that you end up with. And since we're only doing that over one time step, this one describes a Markov chain, a Markov transition model. Now, if there are any experimentalists among you, let me go back. This should be actually very familiar. This is what we do when we do PIV, particle image velocimetry. Right? In particle image velocimetry, we seed particles in the flow, and we take two very rapid laser shots, boom, boom, like this. And then we're going to associate one particle to the next one, okay, over one time step. The time step is the two laser shots, okay. And then we're going to extract not the probability of going from one to the other place, we extract the velocity from that. So this Pij matrix is nothing else than doing PIV in phase space with our hypercubes. Okay? So now this one is replacing, this is encoding the dynamics over one time step. So all the motion of our snapshots is now inside the Pij. So this is replacing our governing equations for a multi-equilibrium system. So what can we learn from P? First of all, P is row stochastic. That's not surprising because all the probabilities have to add up to 1. If you end up in box I, you have to come from somewhere. And if you add all the components from where you come, they add up to 100%. Okay? Once we know that this is a row stochastic matrix, P, we also know that the eigenvalue is 1. Okay? All the other ones are less than 1. And there's only one with a unit eigenvalue, and that's the stationary distribution. So pi p is equal to lambda, which is 1, times pi. And don't worry, the Markov guys always like to multiply from the right. Okay? Okay. So this is our new mean flow. Okay? This is the stationary point, which now replaces the mean flow of the Navier-Stokes equations. Okay? Now, eigenvalues close to 1, that's the next ones down from the stationary distribution, are the ones that don't move very much because each Markov transition is powering out the matrix P, right? And if you have an eigenvalue close to 1, 0.99, if you power that one out, it's not much movement, okay? So those are the distribution of the persistent states, states that are very coherent, very observable, very persistent. The small eigenvalues, as you go down the ladder, they will describe transitory states because that's exactly what we want. We want to cluster everything into persistent and transitory states. Okay? And the associated eigenvectors give us regions in phase space where these persistent states and transitory states hang out. Okay? So what more can we do with the P matrix? The P matrix now we're going to interpret as a graph. Okay? And when you have a graph, there is something called the adjacency matrix that links all the nodes with the weights to other nodes. Okay? Our P matrix can be interpreted as a graph matrix where each box is a node and each entry is the probability of going from one node to the next. Okay? So now, if P acts as an adjacency matrix of this associated graph, we now can actually do clustering. So we can say, how about we introduce, let's say, 10,000 of these hypercube boxes. Okay? And now we want to say, is there a grouping in these hypercube boxes where we can make a community of boxes that actually act very similarly? Okay? And that one is exactly what you do, for example, on social networks. If you look at a social network, you want to see communities. And a community is defined as having very strong links within, but very weak links to the next community. Okay? So we're going to interpret that P matrix raw as it comes out from our hypercubes as a social network, and we want to see cliques. We want to see families or communities. Okay? And that one is done, the gold standard for that one is called the Louvain algorithm. Okay? So if you do that one, you have all the boxes, the ID on all the boxes, box 1, box 2, box 3, box 4, up to box 10,000. And then we're going to lump that together, so all these IDs are in one community. Of course, it's a little bit more complicated. Okay? So when you do that one and you multiply your P matrix, you cluster it. You cluster it down into communities from your hyperboxes. So this is the P matrix, and then if you cluster it down, you actually get little families. Okay? This is a community, this is a community, this is a community. Now, anything inside that box is doing it within the same community, exchanging within the same community. Anything off diagonal, block off diagonal, is a transition between communities. Okay? So these are results from Florence. We have more than 16,000 boxes. This is the raw one that we get. Okay? And then we're going to cluster it with the Louvain algorithm. And then this is just grouping and reshuffling rows and columns to make it as block diagonal as you possibly can. Okay? So this is the first round, and you can already see to the naked eye there's a lot of communities, a lot of blocky things on the diagonal. Now you do it again. You use these ones as one hypercube. Okay? You replace it, you throw out the old hypercubes. Now you have crooked hyperregions in a sense. Okay? And you do it again to go from clusters to superclusters, clusters of clusters. Okay? And if you do that one, you get nicely 4 clusters from our simulations. Okay? And now we can do analysis on that one. This is a persistent cluster. This is a persistent cluster. This is changing within. And then all the black ones are exchange states that go from one community to the next. So if you push this one back to our little spaghetti of bx, by, okay, so here's bx, by, you actually cluster out the 4 regions, and you get also, you identify the regions that have a high probability of going from one community to the next. So if we get anywhere close to a box that has a high transition probability, we have to be aware that this could lead to a change in bx, by, or a change in the reversal of the magnetic field. Okay? So we can even, within the cluster, we can distinguish what is a state that most likely stays the way it is, and what is a precursor for a state change to another cluster. Okay? Another thing that we can do is, and that is very much work in progress, if we put ourselves in one state and we say, what is the best path to go to another state? Okay? We can do exactly that path, because now we have a graph that connects all the ones, and in a graph you can go from A to B, and the best way to go from A to B is a Dijkstra graph. A Dijkstra path, right? Shortest path. This is what your car does from the navigational system. Exactly the same algorithm. The only thing is, here we have to multiply instead of add the length of the path. But you can easily change that one by taking the log of the transition probabilities and just add them up. Okay? But this is work in progress. That has a lot to do with optimal transport and for the specialists among you with instantons. Okay. I'm going to skip over this one. This is the Rayleigh-Bénard problem, rolling either this way or that way. Okay, and you also see This is going through exactly the same thing. We first identify two clusters and the transition clusters between them. Okay? Then we hypercube it. Then we're going to turn it into a graph representation. Then we cluster it. And then in that case, we end up with 6 clusters. The big ones actually split in 2. One wobbles a little bit more than the other, but we could combine them. Okay? And then we have these 6 families, and the off-diagonal terms describe the transition in yellow between one cluster and the other. Okay? And again, we can, for example, identify a dangerous cluster here that is awfully close. It should go back, but it has a high probability of going this path and ending up in the next cluster. This is one you already can predict with quite a good accuracy that the whole convection roll will start to turn around. All right, so this was the first one. Now the other ones will go a little bit faster. Okay, so the next one is I want to talk to you about the residualized latent dynamics and the Moritz-Zwanzig concept. Okay, so what is this? Okay, usually when we have model reduction, we always have a little bit of a closure problem. Okay, this is the key issue in any model reduction application. And the thing is, when we do model reduction, we usually set a point where we, from there on, neglect everything else that comes beyond that. Okay? Think of it like a POD analysis. You look at the singular values, you look for a big drop-off, and then you say, okay, I think the big ones capture everything, the small ones I forget. Okay? Now, for a proper closure, this might not be a good idea to drop everything and throw it away and never talk about these scales again. What you should do is you should actually model the cumulative effect of everything you throw away on the degrees of freedom that you keep. Okay? So this is the idea of subgrid scale modeling in LES. Okay? So here it is. These are the modes you retain, and these are the modes you dismiss. Now, let's go for a moment to go back to linear. What do we do if we have a linear operator? In a linear example, for the moment, we can actually write down an equation for R, the parts that we keep, okay? And then the equation for D, the parts that we dismiss, okay? It's a simple partition, okay? Now, we can actually solve this system because it's linear for the retained modes. I can write this in an equation that only depends on R. Okay? And if you do that one using a Schur complement, and this is the Moritz-Zwanzig formulation, this is the equation for R. There is no D in there. Okay? There's no D in there at all. This is a totally self-consistent, self-contained equation, but the price you pay by wrapping everything that you threw out into everything that you keep is, it's not just a differential equation anymore. It has a history term. Okay? So it turns into an integral differential equation, but that one is exact. Okay? This one I could run forever. This will never blow up on me. Okay? But let's look at this one. This is the retained modes. Now we use the retained modes and bring it from the retained ones to the dismissed ones. Then we propagate the dismissed ones and keep all the information, the history about the dismissed ones, and then we bring it down to the retained ones. Okay? So this is small. Then we're going to blow it up. This is high dimensional, and this brings it down to small. Okay? Expansion, propagation, compression. That's what it is. So if you truncate your system, you basically just do this. If you residualize the system, you wrap the dismissed ones into the retained ones, you solve the whole thing. And this is the influence that you have on the influence of the dismissed scales on the retained scales. If this is small, you probably get away with this one for a while. But sooner or later, if you do really, really high truncations, this thing will be not small, and in the end, this will cause the truncated system to go unstable, or at least maybe go useless. Okay, now, small, high, small. But if you put everything together and just say, this is just the kernel, right? Then the kernel actually goes from small to small. right? You don't need this thing in the middle. This is just writing it out if we know how to do it. Okay? So if it's small to small, can the kernel be identified or machine learned? Okay? And this is where we carry it over to the nonlinear side. So in a linear case, the kernel leads to an upper triangular block Toeplitz matrix. That's what it is. And it can be solved very, very easily. It's called a Procrustes problem. In the nonlinear one, the kernel can be modeled by an autoencoder. Okay? So we just throw an autoencoder onto that kernel, the whole thing, okay, and say, go figure it out from feeding it data. But now, what we do is we're going to imitate the linear design. So this whole thing will be an autoencoder. But remember, this one is an expansion. This is now turning into a reservoir, and this is turning into compression. Okay? Small, high, small. So our autoencoder, even though it goes from small to small, has to have a reservoir in the middle that is rich enough to represent this dismissed dynamics. Okay? So we're going to try that out. This is a joint work with George Rigas from Imperial. And we're going to try that out with doing the harmonically balanced Navier-Stokes equation, just as an example. This is the harmonically balanced Navier-Stokes equations. It has a linear dynamics. It's basically the Fourier transformed Navier-Stokes equations. This is the linear part, and this is the nonlinear part where the frequencies interact with each other through triads. Okay? So I'm going to do an example where we keep 4 frequencies plus the mean flow. So 5 equations altogether. This one is the mean flow interaction. That's the next one, and so on. Okay, so these are all 5 equations for the 5 frequencies that we keep, 0, 1, 2, 3, 4. And then we're going to say, it's already truncated, I agree, okay? But now we truncate it even more. And we say, let's retain the first 2, mean flow and first frequency. And the other ones, we dismiss and wrap into the other ones, exactly the way I told you. Okay? So what we do is we're going to partition our Navier-Stokes equation into low, 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 high, high, low, and high, high. And we know how to do that. We want to have an equation for low to low, okay, only the ones we keep. But we don't truncate here. We residualize everything else. This is the residualization, low to high, high to high, and high back to low. Okay? This is the kernel we're going to learn. Okay? We don't write it out like R's. This is the kernel we learn. Okay? And then if we do that one, this is what happens. So we have to have an autoencoder that goes from low to high, back to low for flow around a cylinder. And the inner part here, usually an autoencoder goes down and back out. Right? This is how we learn autoencoders. This is an anti-autoencoder. It goes down, but in the middle, it has a reservoir here that is rich enough to represent the high to high. And you would say, well, doesn't that go against model reduction if I need a high reservoir in the middle? Well, the reservoir doesn't have to be as high as the degrees of freedom you have, right? Just a little bit, like double the size here is sufficient to give enough reservoir to represent that high to high inverse, okay? And then it learns it, and then it truncates it and residualizes it, and then the residual is represented almost exactly, okay? If you don't have that reservoir in the middle, you do really an autoencoder that is bottlenecked in the middle. This thing will not converge and give you really, really bad results. All right. On to the third one, the dynamics preserving reduction, okay? And that, again, has to do with model reduction, okay? So what we saw if we do model reduction is we need memory terms, right? If you truncate and you close out your dismissed scales and you wrap it into the retained scales, it introduces memory terms, okay? That's one way of dealing with closure. Another one of dealing with closure that is often used is time delay embedding. So you take your snapshots And you don't take just the snapshots, you also take the past history of snapshots and add it as a augmented state vector. Okay? If you do that one, that goes under Ruel-Takens. Very, very popular technique, time delay embedding. The third method is something that is a little bit exotic or neglected, and this is the one we looked for in the computer science literature. There is something called locality sensitive hashing, okay, LSH. And that one looks very strange for now. And hashing is the computer science way of saying reduction, okay, compression. Don't be put off by hashing, okay. And locality sensitive means if I compress my state vector, for example, it has 1,000,000 degrees of freedom, and I compress it down to 1,000, okay? That's the hashing part, compression. And locality preserving means if I take the difference between any snapshot, between my 1,000,000 component snapshots, I take the difference between them, Euclidean. And then I take the difference between the both hashed version, the compressed version of 1,000 only, that distance is the same, okay? So this is preserving what's local to be what's local after I compress it. Okay, so this one goes back to a very important theorem. Johnson-Lindenstrauss is the name of that theorem. Okay, so the idea is, the question is there a way of doing dimensionality reduction for fluid system and embedding that preserves the local distance between all the snapshots the way I have it in my full uncompressed data matrix? Okay. Can I compress it without messing up the relative relation between all snapshots to themselves? Okay. And that one, the question, POD doesn't do that. POD messes it up, DMD messes it up, SPOD, all these things, they all influence space and time. They compress space, but they sacrifice time. Okay. So, and the answer is yes, there is such a compression, and that one goes back to the Johnson-Lindenstrauss lemma that says yes, there is. Okay, the Johnson-Lindenstrauss lemma is an existence theorem, right? It just says yes, it exists. It doesn't tell you how. Okay, typically of pure mathematicians with their lemmas, they say yes, it exists, but they don't tell you how. Okay, so this is the lemma. Phi is the compression. And just what I said, you have your original matrix, okay? You pick any snapshots out of the two, okay? Don't have to be consecutive, can be really far apart. And then you take the difference between them. And then you do the same thing with the compressed snapshots. Same two snapshots, but first you compress them, and then you do the difference. That's the thing in the middle, the reduced space, okay? And then this says that, yes, there is an embedding, there is a compression, that preserves the distance up to a distortion factor of epsilon. Okay, so you get maybe sometimes 1% more and 1% less, but within that bound you stay. Okay, the bounds. Here's the bad news. The bounds. These bounds are observed with a probability above 2/3. So better than 2/3, you preserve it, and once in a while you don't preserve it. Okay, that looks really terrible right now, but there is a fix for that, a really cute fix where you can tune it in anything you want. So don't be alarmed about something that only works 2/3 of the time. Okay, it works much better and it fails very gracefully. So why does that preserve dynamics? So here is phase space, okay, 3-dimensional. These are your snapshots, okay, in phase space, some kind of phase space. Okay, so this is our dynamics. Okay, it spirals like this. Okay, and now Johnson-Lindenstrauss says if I take the distance of any snapshot to any other snapshot, okay, it's that these sticks between all the snapshots. Every single stick in that picture cannot vary by more than 10% in length. Okay, maybe 99% or 1% more. Okay. So if this one cannot move by more than 1% for every stick that is there, this one intuitively preserves dynamics. You can make that more rigorous. Okay, so now the million-dollar question is, what is that magic compression that does all that? Okay, and that magic compression phi is a decomposition that is called PhD. And I did not make that up, okay? This was really in the original paper by Alon and Chazelle. By the way, Chazelle is the father of the Hollywood director, okay? That made all these movies like La La Land and so on, okay? It's the same Chazelle, or the father, I should say. He came up with PhD. Now, at the center of this magic transformation that preserves the dynamics is some kind of a spectral decomposition. You can use a Fourier transform if you want to, okay? We use a Walsh-Hadamard. That's a tiny little bit better, okay, but not by much. If you like Fourier transform, use a Fourier transform. And then you have the randomization. You take a Bernoulli process, and that's a very, very, very sparse matrix. Okay? And that sparse matrix does all the compression, takes some of the wave numbers from the spectral decomposition, and produces a randomized subsampled Fourier transform. That's all there is. It's classical computational harmonic analysis. Okay? Now, there's a little bit of a problem. If I have a sine curve here, okay, my signal is a sine curve, and I go through the h and the p by themselves, okay, then this one does the Fourier transform, right? So the sine curve, just the peak. And this one is a very sparse matrix, so most of the time, this thing, because it's so peaked, grabs a 0, right? It's very unlikely that we're going to grab this peak. Okay? So you cannot have, what we have to safeguard against is a band-limited signal that has a very sparse spectrum, because we need to grab randomly into that spectrum and pull something out. Now, if this one is sparse already, then we mostly grab zeros and we get nothing. Okay? So we need to broaden the sign to have a broad spectrum without losing the sign. And this is what the D matrix does. It's just a diagonal of plus and minuses randomly distributed. So what we do with the sine curve, we just randomly take a point and flip it down around the sign, around the 0. So the sign looks like this. Randomly up, down, up, down, up, down, up, down. You can still see the sign, but if you Fourier transform that now, this is the spectrum that looks after D and H, and then when we grab something, most likely we get something. Okay, so this is just for broadening purposes. So if you do this one, you can compress by quite a bit. As I said, the failure ratio, you can deal with that one. If you want details, please talk to me. I'm happy to show you. This is, by the way, joint work with my postdoc, Anton Glaskov, okay, at KAUST. So then we tried it out. This is Rayleigh-Benard convection in a spherical shell. Okay, this is done with another student from KAUST, Bhargav Mantravadi. Okay, so this is what the whole thing is. Convection on a spherical cell, Rayleigh number 4 million, and we have 2.7 degrees of freedom, million degrees of freedom, and we're going to choose a distortion of 1%. Okay, stick length less than 1%. Okay, now, if you do a regular POD on that one, it takes 157 seconds to get this mode here. Okay? If you do it compressed with the fast Johnson-Lindenstrauss transform, the PhD, okay, on exactly the same data, you get this one in 4 seconds on only 2.3% of the data. That's only what is needed to produce this POD mode. So this one is way, way overdimensioned by the SVD. There's a lot of redundancy of calculations that you could avoid if you compress it down while still preserving the time domain. Okay, so at the moment, we're going to use the FJLT as a linear autoencoder. And we also do the FJLT, that PhD transform, and see whether we can apply that one on the Krylov space and accelerate Arnoldi and Krylov techniques, because in that case, it's not the distance, but the scalar product that you have to preserve as you compress the members of a Krylov space. So this has a lot of implications on many, many other things. And now the last one is the derivative-free optimization. What happens if the adjoint is not an option for you? Okay, And in that case, when we do optimization, we need gradient information, but the adjoint is just hard to write down, derive, or even impossible to write down. What options do you have? Okay, so an alternative is called NVAR, and that one is ensemble variational. And that one goes back to the original part that the adjoint actually replaced. The adjoint, you only calculate once backwards to avoid many forward solutions, right? But now we're going back to the forward solutions, okay? So we take agents, particles, that we move forward through the system. We have control variables, state variables, and observables. So what we do is we link the control input to the observables that we have directly through any nonlinear state. Okay? That could be RANS, that could be LES, that could be DNS, that could be anything you want to. Okay? It could be open flow, it could be your research code, anything you want to. Okay? And then what do? Let's say we want to have a target that we want to push the fluid towards. Okay? So we have an entire N agents that we push forward. We go for the mean of the agent, and now we're going to use these distances as an expansion of our control state. Okay? Once you have that one, you basically assume a surrogate surface of all the cost functionals for all these evaluations. Okay? And once you have that surrogate surface, right now we're not using radial basis function or anything, very simple things at the moment. You can actually write down the cost functional expressed in the spaces. Okay? And once you have that one, you can also differentiate the cost functional, okay, the surrogate surface with the spaces. So what we do is we replace the adjoint gradient by a differentiated surrogate surface that we form from sending 10, 20, 12 particles out there to represent our cost functional. Okay? And once you do that, you even get the Hessian out of there, which is a hard thing to do for adjoint looping. Okay? So now with this scheme, we can accommodate governing equations of varying fidelity. We can mix and match RANS, LES, DES, DNS, PSE, whatever you have, okay? And treat even turbulent flows. Okay? There is no shadowing, there is nothing. There's no Lyapunov divergence of the adjoint when you calculate backwards. All that one is eliminated. So here is where we tried that out. And this has actually been done here at Jussieu by Tarani and Alejandro, and Thomas was involved, Thomas Fulana and Miguel Fosas Di Pando. So this is an example of shape optimization. The objective is the following. We have a wall, a ceiling, that has a sine curve. And on that ceiling, we're going to hang a drop. Okay? With a contact line, everything is calculated. Okay? And then, of course, the whole thing, forms and drops down. And then you have something that is behind and something that drops down to the floor. Okay? And what we want to do is, the objective is, minimize the volume of the falling drop. So we want to have as much as possible hanging out there, hanging on the ceiling, by modifying the shape of the ceiling. Is there a better shape than just sinusoidal? Okay? And you can imagine this is very hard. It has topology change in there, multi-phase, a moving contact line. Writing down the adjoint for that one and optimizing that one is a nightmare. And also, the thing also that you get from adjoints is you always get a local minimum. You never know whether you have a global minimum. Okay? But if you combine the NVAR with a globally converging optimization scheme, here it is, okay? You come down and you see that you can optimize the ceiling shape such that the maximum will actually hang back on the ceiling and the minimum of volume will fall down. Okay? So with this one, let me just summarize really quickly. So I showed you 4 little things, little vignettes about a flow analysis that goes a little bit beyond the normal toolbox that we have. In the first case, we used a Frobenius-Perron formulation to deal with multiple equilibrium points and still get proper information and analysis out of that one. The second one was a residualized latent dynamics with Moritz Wansig. So this is a way of doing really radical model reduction and truncation and still have a stable system. The trick is that when you go down in an autoencoder, you have to provide a reservoir in the middle that is rich enough to represent the temporal dynamics, the memory of the entire system. Then I showed you a Johnson-Lindenstrauss application of a dynamics preserving reduction that is actually very, very powerful to compress your data without messing up the temporal dynamics between all the snapshots. And then the third one was a ensemble variational technique with propagating a bunch of agents, I guess nowadays you would say agents or particles, forward, and then fit a surrogate surface through the cost function and take the derivative of this one to do all the optimization. And this way, you make your way all the way around adjoints or any formulation of adjoints. So with this, thanks for your attention.
Thank you very much, Peter, for this very nice talk. It was too good, actually. Sometimes, you know, when you hear people, you feel like you have understood everything, and then the next day, it's actually not the case. So I feel like
there's a lot of detail left out. Yes, yes.
But it was very nice. Yeah. Thank you. Are there any questions?
Thank you very much for your talk. That's really interesting. I have just a curiosity because related to the last thing that you have explained, the ensemble Kalman filter. Can you give a comment, or in your experience, how can we utilize the ensemble, this technique, in the context of large eddy simulation? Because the system is really chaotic, and I think that you need really much data to optimize. I think instead with the adjoint you can propagate backward, and that's right, but you don't need so much data, right?
That's correct, but how do you actually backpropagate the LES without blowing up on the adjoint if you apply it to LES? There is a positive Lyapunov exponent.
Of course.
You either have a very small time horizon, or you go into shadowing, right? And then you regularize it on the way back.
Of course. Yeah.
That's the two choices you have. Okay?
Yeah.
In this one, you formulate the cost functionals, of course, not in terms of the fluctuations. You formulate it in terms of lower order moments or statistics or drag, you know, averaged out and things like that. And that does the shadowing almost for you, because you never actually go back and run into a positive Lyapunov exponent.
Yeah, of course. But
you pay the price, but if you do the calculations, and you do nonlinear adjoint looping, right? So nonlinear adjoint looping, one loop is 3 simulations. One with a two for the checkpointing forward and one forward, one backward.
Yeah.
Okay, so if you need 10 or 12 full loops times 3, you do something like 30 simulations, right? Altogether to get 10 iterations, and then you're stuck in a local minimum.
Yeah.
Okay, you cannot get global. Here you may do 40, maybe 50. Of simulations with all your particles. Let's say you have 6 particles or 10 particles, and you do forward simulations. So it's not quite there yet, but for the extra value that you get of knowing that you get a global minimum, it's comparable. You know, derivative-free optimizations used to be like 5,000 iterations before you get anywhere, right? And we cannot do 5,000 simulations. But now with these techniques, they get into a very competitive range where they're competing with adjoints. And especially when you cannot formulate the adjoint, this is the only option you have, and it's a very good one.
Yeah. I was thinking about to use the ensemble Kalman filter technique at the beginning.
Yes.
Find several global minimum and then optimize with that joint, even for small trajectories.
Yes. That's a very good alternative. Yes.
Thank you very much.
Yeah, that's a very good strategy.
Any other question?
Thank you, Peter, for the very nice talk. I have a question on the second part.
Yeah.
So these closures for reduced order modeling, that's actually what we need to do when we truncate for very, let's say, very nonlinear systems.
Yes, yes.
To avoid build-up. So you have this time-dependent term, and you try to express it as an autoencoder.
Yes.
And you have what you call a reservoir, which is basically your latent space.
Yes.
Am I correct?
Yes.
Okay.
For the memory term.
Yeah. So the size of this latent space must be related to the number of degrees of freedom in the physical system.
Yes. Yes.
So
correct.
my point is, when you apply this to truly turbulent flows, so you know that the number of degrees of freedom scales like Reynolds number to the power 9/4.
Yeah.
So I was wondering, how much can you hope to capture the closure with the reservoir using a reasonable latent space, or what could you do to extend this to truly turbulent flow, not just
that's a good question.
or this kind of thing?
So the size of that reservoir is not depending on the full degrees of freedom. It depends on the size of the latent space and the decay of your kernel in time, right? And that one, you would have to do an autocorrelation of how long the memory you have, for example, in
So the more
turbulence,
turbulence, the shorter the correlation.
an eddy turnover time, for example, right? After an eddy turnover time, you don't remember anything, right? There's no connection. It all whites out. Okay, and Kartik Duraisamy has done a really nice analysis of closing out an LES with this technique, and then he got away with an incredibly low reservoir. Okay, there has to be a reservoir. If this one is just straight here, it's not going to work. But even 1 degree more in your expansion, in your kernel expansion, with approximating it with just a scalar decaying exponential, so you have an exponential decay of memory, just one time step back, that was enough to show significant improvement. And if you do 2 or 3 or 4 of these kernel expansions, then you're getting better and better.
But, well, still, so you still have, I don't know, like
it's case by
millions
case.
of degrees of freedom.
Yes, that's correct.
Okay.
That's correct. Yeah.
Any other question?
Thanks a lot for the presentation. I wanted to ask you about the dynamics preserving reduced order modeling.
This one, yeah.
I was wondering, because I've seen this being used to, of course, this could be used to generate synthetic data, so synthetic trajectories.
Yeah.
And I was wondering if this could be used to train some kind of other models on top of that data, or what would you use this synthetic data for?
If you want to get the dynamics trained, then this would be a really good candidate because you can train it with low dimensional data and still get the dynamics of the full dimensional data, right? Yeah, that would accelerate the learning.
Okay.
Yeah.
And
I would think, yeah.
And do you
I
think
still
there
have
are
to try it. Yeah.
other applications that you could use if you use this type of models to generate some data that evolves in time? Do you think you could use this data for other applications, or
everywhere where time dynamics is important I mean, originally this locality sensitive hashing was actually used for data that had privacy concerns, right? So let's say you have medical data and you want to anonymize it, okay? So you want to hash it, but you still want to preserve the relational distance between all your samples, so you can do the analysis without knowing who it is. Okay, so this was often used for privatization of data. You have the raw data and then you hash it, but you don't mess up the relational, the relation between the data. Okay, the distance relation between the data, so you can do all the analysis without knowing what it is. That's where it actually comes from.
okay.
But you know, in our case, we're using it for preserving dynamics. So everywhere the dynamics is important, you could actually compress the space down to almost nothing, and still do all your analysis on the zipped file rather than unzipping it. Okay.
Okay.
Mhm.
Excellent.
Yeah. So there must be a lot of applications. We're at the moment we're targeting the Krylov subspace because we want to preserve the relational the orthogonality the orthogonality properties of the Krylov subspace by compressing it but not messing up the orthogonality relation. So we can do an Arnoldi on the compressed file rather than on the full file. That's what we're thinking about it now. Yeah.
Okay, maybe one last question.
Thank you for the presentation. It was really interesting. I also have a question about the residualized latent dynamics, which is actually more of a curiosity. In a slide, when you showed the kernel that you wanted to learn, like you've been very specific on the architecture you chose and the size of the latent space,
Yeah.
but that kernel, now I don't remember the slide perfectly, but it depends only on the difference between t and tau.
Yeah.
So the full integral can be seen as a convolution. So what I
Correct.
see
Yeah.
that people are doing right now in machine learning is to pass to the Fourier space, so that that integral, which is a convolution, because it depends,
multiplication.
it's a multiplication, and so they learn it in the Fourier space, and then they map it back.
Yeah.
So I was wondering if you tried this kind of architecture, like learning in the latent in the Fourier space. Sorry, if it makes any sense to do it here.
We haven't tried that out. There's a little bit of causality issues too, right? You have to have a causality filter then if you do a Fourier transform.
Okay.
With the multiplication, so you don't use snapshots in the future. But I think it can be done. Yeah.
Okay.
I think it can be done.
Okay. Well, thanks.
We haven't tried it yet. Yeah.
Okay, thank you
Thanks.
again, Peter. And Peter is around until the end of the month. So
End of the month, yeah.
That's right. So I guess maybe feel free to contact Peter if you want to talk more.
Yeah.
Thank you again.
Yeah. Thank you.